Okay, so next we're going to take a look at question 10.52. 10.52. And what the question asks us, it says, propose an efficient synthesis for each of the following transformations. You might find it useful to review section 10.13 before attempting to solve these problems. So we're just looking for a synthesis. So synthesis. And in A, all we want to do is take cyclopentane and convert it to chlorocyclopentane. Could anybody suggest a set of conditions for this? To make chlorocyclopentane from cyclopentane. Exactly. Thanks, Kiana. Yeah, Kiana says chlorine and light. Why can we just use chlorine? It's because this compound is symmetrical. So this is the only product we get. Only product. When we have a symmetrical alkane, we can use chlorination. There's no problem with that. In B, we said that there's no way to do an iodination directly, but we want to take, and we want the cyclopentane, and we want to somehow make cyclopentyl iodide. So how would we make an iodide? Well, the only way that we have to do this would be to treat something that has a good leaving group with iodide, because we know that iodide is a good nucleophile. It's a weak base. It's actually a very good nucleophile. And so in terms of retrosynthesis, if we had the bromide, all we would have to do is treat that with sodium iodide. Since it's an SN2, you could pick a polar aprotic solvent like acetone or acetonitrile. You don't have to, but you could, because this is just an SN2 reaction. So that reveals to us how to make iodocyclopentane. So the first thing we're going to do is we're going to convert it to the bromocyclopentane by treating it with bromine and light. And then we're going to hit it with sodium iodide. And again, iodide is a great nucleophile. So very weak base, but it's a great nucleophile. All right. And if you're wondering, could you use chlorination here? So or Cl2, I would say absolutely. Chlorine would be a good enough leaving group, no problem. You could absolutely use that. The next one, we want to take cyclopentane, which seems to be the molecule of the hour here, and we want to convert that into cyclopentene. So we want to make a double bond. But we saw already that the only opportunity we have to react with just an alkane is to either do chlorination or bromination. So let's just pick chlorination, since this is symmetrical, as we just discussed, to make chlorocyclopentane. Now, in order to make cyclopentene, I need to do an E2 reaction. I need to do an elimination reaction, and thus I want to avoid having any SN2 product. If you were to choose sodium methoxide, I would not pick that. That would be a bad choice, because you're going to get SN2, but you're also going to get mostly E2 in that case. You want to suppress any SN2 product. So for that, you're going to use a hindered base, like potassium T-butoxide. You could also use DBU or DBN. Those would work as well. But either way, both of them are going to, or either one of them is going to afford an elimination. So we're going to see the same strategy come up in the next problem, 10.52D, where we take, oh, sorry, no, we're not. We are starting with the alkene, my mistake. So we're starting with cyclohexene, and we want to convert that to the dibromo compound. And remember, bromine is added in an anti fashion. So we end up with this compound plus it's an enantiomer. Could anybody suggest conditions to add bromine? Oh, D doesn't start with an alkene. I thought it didn't. Maybe. Anyhow, so so the first thing we need to do then is we'll just try bromination instead of chlorination. And then we'll do the same approach that we did in the last problem. So we'll treat it with potassium T-butoxide. That's going to give us cyclohexene. Now, how do we add the bromine across that? Could anybody suggest a way to do that? How do you add bromine in anti-fashion? Exactly. My student said, just throw some bromine at it, Br2. And you're absolutely correct, right? We get anti-addition when we do bromination. It proceeds through the bromonium ion, and then we get attack from the least hindered face of that bromonium ion, and we get anti-bromination. Great, anti-addition of the bromine. Okay, let's see. Next one. Let's see here. The next one, so is, oops. This is, scooch up here, 10.52E. We want to start with methyl cyclohexane, and then we're going to convert that to methyl cyclohexene, or 1-methyl cyclohexene, I guess. So 1-methyl cyclohexene. Again, we're starting with an alkane. It's unsymmetrical. The only possibility we have is to treat it with bromine and light. That's going to give us 1-bromo, 1-methyl cyclohexane. And we want to make the Zaitsev alkene. Remember, if we wanted to pull off this proton to make the Hofmann product, which would be this, for that we would use a hindered base, but we want to pull off one of these protons to make the Zaitsev product. So could anybody suggest a base for that? Exactly. One of my students said, try sodium methoxide, Mr. Dion, and I would agree with you 100%. That will give you the Zaitsev product. And there you have it. Okay, next I wanted to take a look at was kind of take a step back here and go to question 10.34. All the way back to 10.34. Okay. Oops. Let me move that out of the way. All right, so now we're going to take a look at question 10.34. And it says identify the major product. So we'll just put here give major product that's formed. The first one is taking 2-methylpentane. So that's this compound. And we're treating it with bromine and light. Well, remember that bromination is selective for the most substituted carbon, which is this one here that I have the highlighter on. And so that's where the bromine is going to go, so that we would get 2-bromo, 2-methylpentane. In B, it says, what would happen if we took the same substrate and we treated that with iodine and light? Could anybody tell me what the answer would be here if I tried iodination with light? Exactly. Somebody just wrote, nothing happens. We'll put here, no reaction, because delta G is positive. Not thermodynamically favored, so nothing is going to happen. The next one, we have C, so we have just some pentane. I think we looked at this one earlier, so I'll go over it a little bit quicker. But if we have pentane and chlorine, well, there's 3 different types of places you can add a chlorine. You could add it at the methyl at the end, the methylene's here, or the methylene in the middle. So there's 3 possible products that could be formed here. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we could put the chlorine here. We could put the chlorine here, or we could put the chlorine here. Those 3 isomers. This is a stereoisomer. So, we could write on this one, we could put racemic for this particular one, but the other ones are not stereoisomers. Next one in 10.34, so this is 10.34D. We're going to take toluene. So this compound, methylbenzene, is called toluene. And when you take toluene and you treat it with NBS and light, you do an allylic, or in this case, a benzylic bromination. Where's the benzylic carbon? It's this carbon right here. So that is where our bromine adds. We end up with this compound where we have CH2, then our bromine. This compound comes up a lot in organic chemistry. It's called benzyl bromide. I was lecturing in organic chemistry too yesterday afternoon, and we were discussing benzyl bromide. This compound is an interesting compound. Does anybody know what the word lacrimator means? Anybody know what a lacrimator is? It has a very distinct effect on human beings. If you've ever chopped onions before and you ever start to cry when you're chopping onions, we'll multiply that by about a factor of 50. Okay, so if you're exposed to benzyl bromide, it's like the effect of onions magnified 100 times. Okay, it's really terrible. It makes your eyes start watering like crazy if you're exposed to benzyl bromide. So I wouldn't recommend it. Next is 10.34E. This one's a little bit more interesting. We're taking this compound. We're taking this compound, and we're going to treat it with NBS like this. Now, the reason why in this case we only ended up with one regioisomer is because you have to maintain the aromaticity of the aromatic ring, meaning you have to have all three of those double bonds in there. With the addition of NBS the addition of NBS to this compound, we have the allylic hydrogen here, and when that's abstracted by the bromine radical, you end up with this radical. Okay, and that radical is resonance stabilized. So you could draw the other resonance contributor like this, like so. Oops, that's not very pretty. There we go. So we have these two contributors to the resonance hybrid, and therefore bromination could occur at either of those positions. Again, the reason why it doesn't occur here, here, and here on the aromatic ring is because you want to maintain the aromatic ring. The aromatic ring produces a lot of stability, but in here we don't have an aromatic ring, and so bromination could occur at this position to give you this compound. Okay, oops, that's not very good. Like this, or bromine could add over here to give you this compound. Neither of these have a chiral center in them, and so those are the only two products we get. And the last one, so this is 10.34F. 10.34F is taking this compound. There we go. Oops. There we go. Son of a gun. Yeah, that's better. And we're taking this and we're treating it with bromine and light. And we know that bromination is going to occur at the most substituted position, which is this one here. So we end up forming the radical at that position. It's not resonance stabilized, so this is our intermediate. And then after halogen abstraction, you add the bromine at that position. I think everybody could have gotten this one. With very little studying, I think most people could have answered that one pretty quickly. So that's all of 10.34.